Okay, all right. So I hope you are all in correct place. So we will be discussing stochastic processes in this summer session, right? So the course number is, so this is, these are new pens, so they just are so thin, writing thin, right? The IE-325, right? So it is stochastic modeling. My name is Savaş, right? Dayanık. And if you need to reach me, so I already collected all this information on one piece of sheet. So let me first distribute this, and then we can go over it quickly before we start today's lecture, right? So you can pass to your friends. No, just pass to your bank. All right. 3 for you, 1 for you. You can have one. All right. So you more or less have an idea, I guess, what this course is about, but I also want to make sure that what you are going to see, a short description is over there. So it's an undergraduate level course. We will to introduce these basic concepts on stochastic processes and modeling, right? Some of the topics that we will be discussing is the Markov chains, the Poisson processes, Markov processes, and you may have not heard much about martingales and Brownian motion before, but I would like to just cover these two topics at least, just to give the basic ideas about them, especially if you are interested in taking courses on financial engineering later during your time at Bilkent, right? And so you see the information about me. So my office is in the engineering building in 214, right? My phone number is 3029, so you can reach me whenever you like to talk with me, or if you cannot make the office hours, which are going to be tentatively between 10 and 12 on Tuesdays, right? If you cannot make those times, then you can give me a call or just send an email, and we can try to arrange some other time to come together to discuss your questions, right? Your teaching assistant is Korhan. You may know him actually before this. I just met him. He's a very nice guy. His office is in 330. Phone number is there. You can reach him again by email. And he decided to keep his office hours on Thursdays between 10 and 12, right? What else? So classroom is here. So if you are here, so you cannot make a mistake, I guess, next time. So Mondays, this is not correct. Tuesday and Thursdays should be our regular class hours, right? Between 1:30 and 1:40 and 4:30. Yeah, textbook. So I decided to follow a different textbook, and it is Taylor and Carlin, Introduction to Stochastic Modeling, right? Unfortunately, the book is not here, so you will not be able to buy a copy from your bookstore because we were too late to order one, right? So how are we going to solve the textbook problem? So there is a copy right now in the reserve section of the library for you to study when you are in library, okay? I also just make copies of chapters, right? As we go along, you can go there and photocopy it for your own notes, right? And it should also be available electronically, I guess. So if you have a printer, you can also print for your own sake, right? There are a couple of other reference books that I find very useful, especially the first one, Sheldon Ross, Introduction to Probability Models, which is quite rich with examples and exercises. And I mean, this course is on modeling, so it is really, there is not a one strict good way to, or it is really difficult to describe how to construct a good model. So what you can do is actually to show a lot of interesting examples, and the students will hopefully just pick up these skills. So the course is more like an art rather than science. So you can actually, it is difficult to really describe how to perform a good art rather than just to show the people actually how you can do it on specific examples, right? And also give people actually a chance to do their own work, like homework problems, right? So that we can just excel on this topic. Therefore, it is important that you do your homework, and I'll also do my job by bringing a lot of interesting or different examples to classroom. So we are not always be talking about the theoretical results, but at every opportunity I'll try to illustrate those ideas on specific examples, right? So how the most difficult part of this course is usually the problems are given in words, in English, without really specifying what the mathematical identity is that you need to do in order to solve the problem. It is actually our job to translate the problem from English to some mathematical model, right? So students usually find that part very difficult. And otherwise, once you do that transformation properly, the rest is just elementary mathematics. You just multiply, sum, divide. You use the usual stuff to solve the problem, right? So, as I said, in order to really learn how to do this translation, well, it is always, I guess, I find it a lot more effective if you bring different examples to classroom and just discuss them, just to illustrate how you can actually proceed with it. There is not, usually in these problems, there are always more than one good way to solve the problem. All I will do in the classroom is probably going to be just one of them, just to propose one way to solve the problem, right? And even you can actually, I'm sure, produce better solutions than I can probably provide in the classroom, right? So it is always, I always encourage students to just participate, just ask questions. If you have another idea, an alternative way to approach the problem, please bring it forward and let us discuss it together. Right? So that also enrich actually our experience. So you can your colleagues, right, your friends can also see actually different ways to solve similar problems. Right? Sheldon Ross, and unfortunately Lawler's book is not in our library. I'll use one chapter from this book when I'm going to distribute it. We will discuss a chapter on martingales. Unfortunately, it is not here, but I can provide it to you. Right? Sheldon Ross and Erhan Çınar's books are going to be on reserve as well, so that you can go there and do exercises. From time to time, you will see that I also pick exercises from these two books. So I am not going to strictly stick to our textbook. But most of the time we will make sure that all the important ideas are covered from the textbook. But I'll also just enrich the discussion, try to enrich the discussion by bringing other problems. Okay, course requirements. Course requirements. So we'll have a weekly homework assignments, right? Starting this week, toward the end of the class, well, next time on Thursday, I guess I'll better know actually how much material we will have covered by then. Then I'll give the first assignment. Assignments are going to be due Fridays by the end of the day, right? By 5 p.m. I would say in the United States now it's the 17, right? Okay, in the afternoon at 5. So this is, I guess, the usual practice here. So the TA is going to keep a box in front of his office door. So you're supposed to put your papers into by 5. Right? Okay, these are more like actually directions for myself, I guess. Yes, you understood them a lot better than I figured out at the beginning of this semester. So we have time only for one midterm. We have to give a final, so we'll do that as well, right? And for announcements, right? So we'll just keep a course homepage, and we'll put the homework assignments in case you're unable to come to the classroom to pick up the questions. The assignments will be over there, so you can always check them, as well as the solutions. And for unusual or that usual announcements also, that's going to be the place that you have to check with, okay? Grading policy, so it's just tentative at the moment, so I don't know what the habits here. But I am just thinking like giving 30% to homework, 30% for midterm, and the remaining points will go for final, right? Now you see the course outline there. This is quite an ambitious course outline, even though it looks like it less than one third of the page. We'll start with probability review today, right? We'll just make sure that you remember all the basic concepts from probability theory. We'll discuss random variables, expectations, and in particular conditional expectations. You will realize over time that actually the stochastic modeling and processes are all about actually conditional expectations. So given some information, what can I say about something that I haven't observed yet, for example, right? So we have limited information. We would like to make the best use of it in order to make decisions, right? And we'll see a lot of examples of that. And then, what else? So Markov chains, we will learn first step analysis. Random walks are ubiquitous in operations research, financial engineering, so we will take a look at them as well. Long-run behavior of Markov chains are usually the way you approach in operations management to solve performance measurement problems, so that's an important topic that we will cover. Poisson processes, if you have ever come across like queuing processes, you must have already seen that they are also important to model queuing processes in general. What else? Continuous time Markov chains is actually just a generalization, an important generalization of Poisson processes. And Brownian motion, well, Brownian motion, these are usually, they belong to advanced class or graduate classes, but as I said now, all the material, especially the students, undergraduate students would like to learn. Now, demanding this material to be kind of introduced in undergraduate classes as well. So you might find it a little difficult because it's a difficult material. There's nothing wrong with you. So I'm just going to try to make it easy for you to grasp, right? And I hope that you will appreciate it over time, right? And Martinez, likewise, even today, I guess, either today or on Thursday, you will see an example of it. They just come across in a very natural way, right? And yeah, so that's kind of the program that I have in mind that I hope that I will be covered by the end of this summer, right? Do we have any questions about the course? Anything about what I want you to follow, all the structure requirements are all clear? Huh? All right? Okay, so I haven't checked yet, but if the library stuff is really correct, so the copy of the first chapter should be ready. So you may just want to get a copy of, or photocopy or Xerox it, all right? And start reading, especially the first chapter, which is going to be about the probability theory. So it's more like a review. You will see a lot of familiar topics in it, but even if you don't like reading the entire chapter, I suggest that you just proceed quickly to the exercise and take a look at them, just to make sure that you can do those exercises, right? If you are unable to do that, then that means that you need to spend a little bit more time in order to just beef up the material, right? So I'll, of course, try to be helpful by assigning especially interesting exercises, right? And I should also just actually emphasize that you should use the office hours whenever, well, at every opportunity. Even if you think that you have some idea how to solve the problem, it is always a good idea to come to office hours. Why is that? This is especially true for this course because it is a modeling course, as I said. So you may actually you may be able to come with a working model, right? But that doesn't mean that it is probably the best one or the best way to solve the same problem. Even if you had a way to solve the problem, just come to the class, come to the office hours to discuss your solution. And it is completely fine with us. It is not that we always cure if somebody just becomes very ill. It is not like that. So it is always good to have you in the class, in the office hours to discuss. And that will also help me to understand actually how you proceed, what needs you have, so that we can actually just make the lectures a lot more effective for your teachings. I also need to remember how it is like to be a Bilkent student, right? So you are always welcome to come to office hours, right? Okay. So probability, right? What is this about? So you remember perhaps from your lectures on probability, right? Now you start something like that? No, probably not. So you would just start with a sample space, right? Right? And a probability function, right? And in this course, you may occasionally see another letter that sits in between this thing, and it is going to be just the collection of interesting events. All right? From this labeling, you may now realize that actually not all the subsets of sample space are interesting for us. Sometimes we would like to just forget about some of the very uninteresting ones in order to make our life to assigning probabilities to those events easier. All right, and I'll say more about them later. When you are given any probability, right? So if you are given any probability experiment, right? Right. So then you start by figuring out what the sample space is going to be, and what is that? It is nothing but just set of all outcomes, all possible outcomes of the experiment that you are interested in. An example for an experiment, a dry one could be just rolling, right? A die, right? Right? And then it could be actually more interesting ones like, for example, the accidents, right? Number of accidents perhaps. Okay, let me just raise this. Right? For example, if you are in charge of just regulating the traffic, right, on Bilkent Road, you will want to do so in order to decrease the number of accidents over time, right? So that is something that you cannot control over time, right? So the future is going to be uncertain. How many accidents are going to take place, right, in the future? So that's like an experiment for you. So you don't initiate that, but it is just because it is uncontrollable by you in the future. So you will want to just start by enumerating all these outcomes, then assign the probabilities, like actually what is the probability of having more than 3 accidents on the same day on the same road, right? Things like that. So an experiment could be, as I said, the number of accidents, right, on Bilkent roads, right? Or the road that connects Bilkent to Ankara, for example, right? Right. So examples for interesting events, right? For example, F here, right, contains empty set, right, which stands for what? Impossible event. Right? We will usually call it not an empty set, but just the impossible event, right? In probability language. Whenever you have an interesting set event, right, in F, then we will always make sure that its complement, which is the difference between F, right, and the sample space, right, is also contained in F. Right? So something happens. If it is interesting to know probability of whether something happens or not, then you will also be interested in knowing the probability of that event does not happen. Right? So we usually have these very natural rules. Right? If there are a couple of things that you find interesting, right, interesting to assign probabilities to those things, right, then, right, you may also be interested in knowing that at least one of them happens. Right? That's the union, right? So events F1, F2, and so on. If they are given, so how do we read this? This is that one of those events, at least one of those events happen, right? So that's also important, right? And then this probability is nothing but just a function, right, that assigns, right, numbers between 0 and 1 to each one of the sets in this set of interesting events, right? So here, for example, f, right, could have been, right, there is at least one, right, at least one accident on the road, right? You find it interesting because that just, right, so then you have to just organize the emergency vehicles to just go there and help people who are affected from this accident, right? If you are interested in knowing the likelihood of having at least one accident, you will then also be interested in the complement of this thing, right? The probability that the complement of this event is going to happen, which is just negate this thing, right? There is no accident, right, on the same road, right? When this happens, you should be happy, but at the same time, you will also want to know actually how you should organize the emergency vehicles when there is no need for them, right? You may want to just send them away to somewhere else, or you will just want to organize all of these emergency vehicles in such a way that they will also be used for emergencies at other parts of campus, right? Therefore, if you are interested in F, you will also be interested in F complement, and therefore, if you are willing to assign a probability to F, then you will also want to know what the probability that its complement will happen, right? And what else? And similar, you can just develop similar ideas here, right? And then, now the probability has what kind of a role? It assigns numbers to these things. In probability, usually we are not interested in how to find those numbers. So usually they are given to us, and then we start to calculate, make calculations about more probabilities for more complex, more complicated events that can be written in terms of these basic events, right? And the important things that you have to remember about the probability, right? So first of all, you see that probability cannot be negative. It is always non-negative, and it cannot be bigger than 1, right? Why am I saying such things? Well, sometimes I ask a question and students just do calculations, half a page or 1.5 page, and they come up with a number which says the probability of this event equals minus 0.4. Then I realize that they don't really think, or they just get lost. Maybe the calculations were so difficult and they never paid attention to the final result. So they could have actually, right, said to themselves that there must be something wrong with their calculations. So it's important to be aware of such basic facts, right? So you can at least check actually whether you are on the right track or not, right? So the other important thing is if the events that you are dealing with are pairwise disjoint, right? Right? What does this mean? You take any two of these events, fi, let's say, I for any one of integers, and fj, right? Right? If I and j are different, of course, the intersection is going to be empty, right? So if this is true for every I and j, right, then, right, if you want to calculate the probability that at least one of them will happen, right, and if they are disjoint, in fact, this is like saying what the probability that exactly one of them is going to happen, can be calculated if you know of the probability of each one of these events by doing what? You just sum them up, right? Okay, this is true for any sequence of pairwise disjoint events, right? So you will see that we will be making an extensive use of these two simple properties. Okay? They are known as the probability axioms. They are called axioms because we don't argue whether they are correct or not. We just assume that they are correct, and then we make on and on the use of all these things in order to solve, as I said, more complex problems. Right? Okay. Another important concept is the independence of events. So if you are given again F1, F2, and so on, when I say and so on, so there is no end to this list, right? So for any finite n, there are that many events, right? So there's a sequence, a countable sequence of events like this going, and they are called independent, right? Right? If they satisfy the following property. So you take any integer n, any integer you like, right? Or I should say for every integer you like, right? If for every integer, positive integer n, and any integers I1, I2, and In, so you're free to choose n integers that I don't specify them, right? 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 You have the following property. You look at the probability that event I1 happens at the same as event I2, Fi2, and they together happen at the same time as event f of In, right? And you look at the probability of this thing. So all these events happen jointly together. If you can find this probability by just first finding marginal probabilities and then multiply them, right? So this times now the probability that event Fi2 happens times finally event Fin happens, right? So what exactly is happening here? You are free to skip some of the events while you are forming these intersections, right? In order for a sequence of events to deserve to be called independent, you have to check for every integer n, and for every choice of integers, indices, right, possible values, that this is true, this equals to this, right? If there are only finite many of them, right, so you must have seen this before, right? You will recall, right? You will recall that, for example, F1 and F2 are called independent, right? If, right, probability that F1 happens at the same time as F2, right, is the same as probability of F1 times probability of F2, right? You remember this. When there are three of them, F1, F2, and F3, right, are all independent. Now things are different. It is not enough, right? Not, okay, enough to say that, okay, the probability that F1, F2, and F3 happens equals the same, well, because this probability equals to the product of the marginal probabilities. So this equality should be true, right? It is necessary to have this equality in order to say the three events are independent, but not sufficient. Not sufficient. Therefore, I said not enough. You also have to check, right? F1, F2 alone, right? If the probability that these two happens at the same time has the same probability as the product of these marginal probabilities. And in fact, you have to just repeat this, right, for every pair. So here F1, F2 together happens. Okay, it should be given by this. F1 and F3 happens at the same time with probability given as the product of the marginal probabilities. And what else? And finally, we also have to check, right? Well, now it's the turn. We have to check this, right? Right? So this is a long list. And imagine what kind of a list you will get if you start with 4 events. So instead of we just use this awkward notation, which basically says, if I just use the same idea here, we would just say that for every integer, right? Here, I have only a finite number of them, right? For example, take this one. For every n, 1 doesn't count actually. 2 and 3, 1 will give you just a trivial thing. Well, okay, why don't I just write that so that I don't want to make exceptions. Right? For every integer n, 1 and 2 and 3 in this case, because I have only 3 of them. If you say 4, you can just actually add something else. Right? And I1, I2, well, I should say I1 through IN, right? We must have what? The probability that Fi1, right, through Fin together happens with probability equal to what? There's product of the probabilities. Okay? And now, when n equals 2, this thing, if you just generate all possibilities, they will give these things. Right? When n equals 2. So when n equals 2, this thing will give just this statement, these three statements. When you just set n equals 3, well, with 3 events, there is only one way to choose I1 through I3, and that will give just this equation, right? If you have infinite number of events, well, there is not a natural integer like here that you can stop and just write all these statements. Instead, for every integer, and you will just come up with finite number of integers, and you have to just write and check this thing, right? That's going to be important for us because the stochastic processes we will be dealing, right, so are usually going to have a countable number of events in it. So I'll be using this notation, right? Right? Is this clear? The notation, what I'm trying to say, right? With independence, okay. And we can also talk about what? Conditional probability. I'll spend more time on this. And what is this? This is, for example, the conditional probability of, right, B given A, right? That's the notation, right? So conditional probability of event B, right, given event A, right? First, that's how we denote it. We don't read it like the probability of B slash A. There is nothing such thing, right? But how do you read it? Probability of the event A given, right? So this is given, that given event A. Even this is the short way of saying that this is probability that event B happens given that event A has already happened, right? If somebody tells you that, okay, there are, well, okay, that event A happened, so you still would like to know now, if that, given that additional information, what can you say about now the likelihood of B, right? So there is, in general, there might be in general a difference between probability B, when you don't know whether event A has happened or not, and the conditional probability of B when you are now assured that event A has happened. All right? Right? For example, B could be probability that an event has happened, an accident has happened, right? And A could be while the time was dark, while it was dark. So given that it was dark, the probability that an accident has happened might be higher than just when you don't know what, whether it was dark or not, right? Or A could be, for example, some indication or information about the road condition, right? Given that, for example, A could be just, it is today or at the time that we are talking that weather was rainy, right? Given that it was rainy, right? What is the probability that an accident happened? You expect this to be somewhat different, right, than the probability that an accident happened without knowing anything about what the road condition was, right? That's especially true, in general it is true if events B and A are not independent. We will see in a moment that if they are independent, then you don't expect any change about what you believe the likelihood of B is if you are also provided information about whether event A happened or not, right? So anyway, so that's the notation. Conditional probability of event B given that event A has happened. And by definition, what is this? So you may see me writing like these two dots sometimes in front of equality. That means this is just defined by whatever I write on the right-hand side, right? If I don't write it like this, if I don't forget, of course, if I write it like this, then that means this equal to somehow need a justification. It should be just justified by using some other knowledge that you have about the concept, all right, we discussed, in order to tie these two ends of the equality, all right? And now, this is by the definition. Now, what is it? It is the probability that A and B happens at the same, right? A and B happen at the same time, divided by the probability of which event? Huh? A. Some of you think, what is it? Do you agree? Is A or B? Which one? Huh? It is A, right? Whatever the event is you are told has happened, you take that probability and you divide the numerator by the denominator, right? That's how you define it, right? Okay, but of course, technically this is true if you can divide, and you can divide only if the number in the denominator is different than 0. But the probabilities are non-negative. If it is different than 0, it should be positive, right? So it is, conditional probabilities are defined whenever the probability of the event that you are told has happened has positive probability, right? It is given by that, and it is, right, just left as undefined otherwise. All right? That's a rule. We really don't care what happens here. You can just, if you, in the calculations, you need to use this. If that is the case, you can just throw any number here. It is not going to bother us. We'll see examples of that, right? And there is also total probability law that is important to remember for us, right? So suppose that this just denotes your sample space, right? I just collect all possible outcomes of my probability experiment, right? So think of this number of accidents on the road, right? And then suppose somehow you can just partition this sample space into disjoint subsets, right? And I'll give names to this one. I don't know, should I stick to this one like A1, A2, A3, right? It goes like this, right? So for example, AK could be, right, the number of accidents, right? Right? Equals K, right? So they are disjoint because number of accidents is going to be either 3 or 2 or 1 or 0, right? So they don't have any common element. They cannot have a non-empty intersection. Okay, this is one. Let me put 0 here. With this example, I guess 0 is also possible, right? And then if there is an event, let's call it by B, right? For which you want to calculate the probability if event B is the one that you are really interested in, right? And you want to know what this is. And there are many cases where, well, unconditionally it may be very difficult to find the probability of B, but if you are further provided exactly how many accidents happen on the road, then you may be able to give a better answer for that one. If these are known, then there is a way to calculate this out of these numbers, right? And it's not a magical thing, right? And actually, I don't want you to really memorize these things. Whenever you need something like this, you can always draw that picture and then argue like this. Okay, I want to calculate the probability of this event. But forget about probability first. What is this? B is, of course, a subset of what? The sample space. Anything that can happen, right, has to be part of omega, right? So that's, what do we call this thing? This is omega, right? This is true. Why? Because B is a subset of omega, right? So small set intersected with big set, of course, gives the set small set itself, right? And now, we will make life a little complicated or seemingly complicated. So omega is what? It is the picture tells me, right, omega A consists of the union of disjoint sets A K's, right? So K starts from 1 to, 0, okay, let's make it 0, right? Like this, right? We agree with this, right? All I did is to rewrite this part. Well, you have an intersection with the union, so you use the distributive law, right? You distribute this thing, right? So it is like the product, and this is like a summation. Right? The product with the summation is what? Sum of these individual products, right? So we can write it like this, right? And now I have this. Now when you come to this point, you also make a mental note of the following. So you remembered it by definition, right? We said these are disjoint. Well, pairwise disjoint. But even after you intersect each one of these with another set, all these things, if you regard this as one single set, right, and index with k, right, you could have called these things, for example, b sub k, right, for every k greater than or equal to 0. These are also what? These are also pairwise disjoint. Right? Right? Is this clear? So if, right, B intersection AK is just a subset of AK, right? And AKs are separate from each other, and the two subsets that you extract from these disjoint sets cannot have anything common to each other, right? So we said there is, right, this is like A1, this is A2, for example, then B comes into the picture, right? So this is the first intersection, this is B1, and then you have this is B2. Since A1 and A2 A1 and A2 don't have any common elements, B1 and B2 cannot have any common elements, right? That's just quite natural. Why do I need to make a note of this? Well, now it is time to calculate the probability. If B equals to the union of all these, right, then, well, right, let me write it like this, right, we call BK. Now you also know that these are what? The pairwise disjoint, and then you remember this property of probability, right? If you are given pairwise disjoint sets, the probability that exactly one of them happens can be calculated as what? The sum of the probabilities of individual events, in this case, like this. Right? I sometimes forget to write these things, but if it is not there, it is clear that I am actually using the same stuff, right? There is nothing, there is no change with it. But then you remind to yourself what this was, right? This is B and event AK happen, right, at the same time, probability of that event, right? Now, well, okay, where am I? Now, I said I know these numbers, right? But this doesn't look like anything like this one. But then you say, well, wait a minute. So, see, this can be written like here, right? So let's write it here. So we said that we know what this is, but this is connected with this probability. In fact, this just lives, right? Sits in the numerator in the definition of this. We have that. Then you can just calculate this by doing what? Multiplying this conditional probability with the probability that event AK happens, and the probability event that there will be exactly K accidents, right? Right? For example, okay, we didn't give a name. For example, we could have defined B as that it is raining, right? So we are just going the other way around. So it is raining. What is the probability that it is raining? Well, you can probably make a better inference or come up with a probability if you are further told what happened on the road, for example, right? So we could use this thing. This has a name. They call this thing as the total probability law. Well, it is too fast. I wrote it too fast, right? Total probability law. Well, there is nothing for this to be a law. It is just a plain logic, right? And we only use the definition of conditional probability, right? So I always prefer to forget this because there are more important things to store in your memories, right? Whenever you need, you can always argue like this to find the formula anyway, right? Okay, too much algebra. Let's look at an example, right? Okay, this should come from your textbook, right? Let me state it. Okay, so let me quickly read it, then I'll just take short notes for you to follow closely. Okay, it says gold and silver coins are allocated, all right, among 3 urns, all right, labeled by 1, 2, and 3. All right, 2 kinds. There's the precious gold and not so precious silver. They are put in 3 different urns with different labels, right? We label them from 1 to 3, and we are also given the exact composition of these urns. So each urn contains different number of gold and silver, right? So there's gold and silver coins, right? In urn 1, urn 2, and urn 3, all right? Okay. In urn 1, okay, the number of golds in these urns are 3, 4, 3, and 6, right? And number of silver coins are like 8, 9, and 6, respectively, across all these urns, all right? So here is an experiment described as explicitly, right? So in this thing you see nothing random, right? So we already know how each of these urns are decomposed into gold and silver coins, right? But then somebody comes up with the following experiment. An urn is selected at random, right? So there are 3 urns. You select each one of them with equal probabilities, right? And then a coin is selected at random from that urn, right? So a priori we don't know which urn is going to be selected because there is an intermediate stage where we don't know what the outcome is going to be, right? But anyway, after you pick an urn, then you pick a coin, and then we would like to know, right, the probability that you must have selected the most precious one, namely a gold coin, right? Okay, you may be given a reward just because you were able to select the gold coin, and then you will want to know what the likelihood of really getting that reward, right? So experiment was what? An urn, right, is selected at random. That's the first stage, and then the second stage is what? A coin is selected from that urn, right? It's a very typical way that a lot of conditional or sequential procedures actually happen. We will see that. Like the way you choose a course to take. You take your course today, it determines what other courses you can pick next semester, right? So there are some courses that require whatever you are taking right now as a prerequisite. If you don't take it now, then you know that you will not be able to take it next semester, right? If something goes wrong and you cannot finish the course today, that also just puts a shade actually about, or makes your plans for future also uncertain. Something like that, right? There's an intermediate random experiment that kind of determines the likelihood of what the final stage of this experiment will result in, right? Okay. That's kind of a very simple example. Okay, no mathematics, nothing in it. So you have given a statement, a description of the experiment, and then you are asked to calculate something, right? Like, what is the probability of selecting a gold coin, right? And our first task is what? Just to translate this problem into mathematics and then use what we have already learned by now to solve the problem, right? Okay. In such things, you start with what? First, it's a good idea to define events, right? What are the interesting events? Well, especially in order to solve this problem, right? Well, we we need to know, right, which urn is being selected, right? There are three possibilities, either 1 or 2 or 3. Let me use these characters again to denote the events, right? Right, the event that earn 1 or 2, right, or 3. I am defining 3 events, right, but I am lazy to, I write all of them in one sentence, right? So I stands for the event that earn 1 is selected. This 2, right, stands for the event that the earn 2 has been selected. Let me put it like that, right, at the first stage, right? And I'll just write it like this, selected, right? What else? What else? Okay. Definitely I am interested in event G, which we can define as the event that a gold coin is selected in the second stage, right? A gold coin is selected, right? At the end, right? Right? We want what? The probability of event G, right? We already know the probabilities of all these events, right? What are they? So we want that. We also need to now, in order to find that, we have to figure out what we know, right? What do we know? We know the probability of selecting earn 1. We also know the probability of selecting earn 2 and probability of selecting earn 3 as well. We know that all of them are equal to 1/3 because we are told that an earn is selected at random, right, with equal probabilities. What else do I know? What else do I know? Huh? Are there any other probabilities that we can say, but right away I know what this is? So finding this thing is difficult because you don't know a priori which earn you must have selected, right? But if I told you, for example, okay, earn 1 was selected, can you now tell me what this probability is? Huh? What is it? Huh? Okay. You are just, simplifying the answer, but just let us give the plain answer first before we simplify anything. So you look at earn 1, right? There are 4 goals. Out of 12, the probability of selecting 4 is going to be this, right? And it is 1/3, that's true. And similarly, you can also calculate what? The probability of selecting a gold coin if you are further told that you actually have picked, right, the second earn. And by the same argument, it is going to be 3/3 plus 9, right? There are 3 gold coins in earn 2, and total number of coins is given by the sum, which is again 12, right? So with this additional information, life was a lot easier, right? Although it was difficult here at first. We don't know actually what's going on because I don't have this additional information. Well, do the same before we go further, right? This one, right? If you are told, right, instead that, well, earn 3 was selected in the first stage of the experiment, then having selected a gold coin is going to be 6/6 plus 6, which is 12, right? So these are all what you are able to infer by just studying the statement, description of the experiment, right? So that's what we are going to learn in this class. So this is a simple example. There will be lots of things told to you without introducing any letters, random variables, or events. It's going to be our job to introduce, first define the important or the appropriate events, and then translate all the given data in terms of some model, so this is a small model, and then use these things to find what is asked, right? Right? I am already over my time, I guess, right? It's first lecture. So let's have a short break. What is the usual time? 10 minutes? Okay, let's give a 10-minute break then. Let's complete this and then go on with other examples.